several years by now. All right, thank you for coming. I will present work on a unified Erdős-Pósa theorem for cycles in graph labeled by multiple abelian groups. This is a talk about the results of two papers, one of which a large number of you have already heard about when Kevin gave a talk about it 11 months ago. But of course, I don't expect anyone to remember that talk in detail. It is so I will go over all the exposition for this as a standalone talk, but in proof sketches, I will not focus on the parts that Kevin already talked about, but about other parts. But if you have any questions, feel free to interrupt me at any point. And yeah, so this is joint work with, so both papers are joint work with Kevin, Oh-Jong, and Sangye. The first paper is also joined with Kenichi Kawarabayashi, and the second paper is joined with Yomoyo. All right, so all of you probably know the theorem, the seminal theorem by Erdős and Pósa, but let me remind you anyway. So Erdős and Pósa proved that there is a function satisfying the following. For every positive integer k, every graph contains either at least k vertex disjoint cycles or a set of vertices of size at most f of k, whose deletion makes the graph into a forest. So a vertex set that will hit all the cycles. And they actually proved that the function is of order k log k, but that's nothing that you need to remember for this talk. Our functions won't look as nice, and I will not tell you how badly they look anyway. Okay, this theorem started a long area of research about this type of packing hitting set duality, which I mean isn't like strict duality in the sense that those have the same size, but at least that there is this duality type statements. And to do this, let me introduce the term Erdős-Pósa property. So in this talk, while other people have considered other subgraphs than just cycles, in this talk we only concern ourselves about classes of cycles. So we say a class of cycles has the Erdős-Pósa property if there is such a function f, so that for every integer k, positive integer k, every graph either contains a k vertex disjoint subgraph isomorphic to one of the cycles in the class, which is a packing of cycles in the class. I will use that terminology later. Or a set X of vertices whose deletion leaves no subgraph isomorphic to that class, a hitting set for that class. And examples, what people looked at are, for example, even cycles. So if we now give our cycles constraints, then and only look at even cycles, then those have the Erdős-Pósa property. Also, if we only look at long cycles, so cycles of length at least k, or combining this even cycles of length at least k, and all of this was proven by Neumann-Lara in 1984. And Thomason, a couple years later, proved this for cycles of length 0 mod k, that those satisfy the Erdős-Pósa property. And there are many, many more examples, and Jean-Florent Raymond has a nice website summarizing these if you are interested in what is known and what bounds are also known. So this is a really great summary for this if you want to look at it. Yes, you do. Yeah. If you would have my slides, you could also click on it, I think. Okay. Right, but not all classes of cycles, these types of constraint cycles, satisfy the Erdős-Pósa property. For example, odd cycles. Lovash and Schreiber found this counterexample here of so-called Escher walls. So what do we have here? We have a wall, so that's like this subdivision of a grid. Let me subdivide it in a way that all of these degree 3 vertices have even distance to each other. And then I add a set of paths between these vertices on the bottom and these vertices on the top, and in a like crossing way. So imagine this, for example, embedded in a surface with a cross cap. So the bottom left vertex here is connected to the top right vertex, and so on. So you go here from the left and go here from the right. And these dashed lines stand for paths of odd length. Now in this graph, this Escher wall, so Escher after MC Escher. So if you have seen any of the artwork of MC Escher, you may have an idea why we call this an Escher wall. He liked to draw these perspective type things. But yeah, so in this graph, we do have many odd cycles, but the wall itself is bipartite. So all these odd cycles have to use actually an odd number of these crossing paths around it. And so here we have an example of such an odd cycle. And since it does kind of use an odd number of these, at some point we have to close our cycle to really cut across the wall like this. And then you maybe already see, not the formal arguments, but why this prohibits there be another odd cycle disjoint to this, because that cycle would also need to cut through it, but then it would cut from this side to this side because of the nature of this crossing linkage. So no two cycles we find in this wall that are disjoint, but of course the wall contains a lot of these odd cycles, because every small hitting set, small now in terms of the wall, which we can make arbitrarily large, the size of the wall, we can avoid in this wall, because the wall is has a lot of external connectivity. Right. Everyone good with this example of Escher walls? All right, but Bruce Reed later proved that Escher walls do contain, while they don't contain two disjoint cycles, we can still find a half-integral packing of many odd cycles, where half-integral now means we do find a set of k cycles in such a way that they are not disjoint, but in such a way that every vertex of the graph is contained in at most two of the cycles of the half-integral packing. So I illustrated this half-integral packing here with colors. So as you can see, every vertex is really just incident with at most two colors. So here we have our k, where k in this case is 1, 2, 3, 4, 5, 6, 7, our half-integral packing. And what Bruce Reed actually even showed more is a structural type theorem like this. So he showed that there's always now a two-valued function satisfying the following. For every pair of positive integers k and h, every graph either contains a packing of odd cycles of size at least k, so the packings of size at least k, a hitting set of size for all the odd cycles of size f of k comma h, or an Escher wall of height h, which then, as I illustrated, will always contain this half integral packing. So this Escher wall is really, in some sense, the only reason why we wouldn't have a packing. So in some sense, it's an obstruction. It's not an obstruction in the sense that containing an Escher wall prohibits that we have our odd cycles somewhere else, but at least if we don't have the packing and don't have the hitting set, then we will always have an Escher wall in there, which cannot have the packing or small hitting set itself, at least. All right, and from this we can immediately see what Reed and Birch then observed a year later, that if we restrict the class of graphs from all graphs to planar graphs, these Escher walls, of course, they are not planar, so they cannot really appear as the obstruction, so the full Erdős-Pósa property would work. And similarly, Thomason showed a year later that if we restrict ourselves to high connectivity graphs, we can also get the full Erdős-Pósa property. But this is, so in this talk, I don't want to do similar restrictions, so these are just some side notes. Okay, so much for odd cycles for now. Let me talk about other examples for the Erdős-Pósa property. So people were interested, for example, in so-called S cycles. So for set S, we look all the cycles that contain vertices from some prescribed set S. And Kakimura, Kawarabayashi, and Marx proved that S cycles satisfy the Erdős-Pósa property. Similarly, you can combine this with something else that we already knew. So we talked about earlier with long cycles have the Erdős-Pósa property, and Brun, Joos, and Schout proved that long S cycles have the Erdős-Pósa property. And Hyun, Joos, and Wallen then generalized this to so-called S1, S2 cycles. So cycles that intersect two prescribed sets, S1 and S2. But do we have more counterexamples now for the Erdős-Pósa property? And yeah, of course, odd cycles were in counterexamples. So of course, odd S cycles will also be a counterexample, because S could just be all possible vertices of our graph, and then it would just be odd cycles. But in difference to the odd cycles, a new obstruction appears, which I want to highlight here. So again, we have some sort of wall. Again, imagine the wall subdivided so that all of these, what we call nails of the wall, so these subdivision vertices highlighted here, have even distance. And then we have some set of these paths, which we call handles, down here on the wall, arranged in such a serial way. And each of these paths should contain a vertex from S. And then we have here on the left paths which are like attached in this nested way. And all of those should be odd. The ones down here should all be even length. And then, as in the Escher wall, we need an odd number of these handles from the left side of the wall. And this is just something then which we cannot find, again, disjoint cycles. So in this example, again, not two, but Kakimura and Kawarabayashi proved that these odd S cycles still have the half-integral Erdős-Pósa property. And again, here is highlighted as half-integral packing of these. Okay, let me tell you about one other counterexample. Now we looked at S1, S2 cycles, which had the Erdős-Pósa property. But if we increase by one more set and look at S1, S2, S3 cycles, so cycles containing vertices from all these three sets, we don't have the Erdős-Pósa property. And another type of obstruction appears, namely something like this. Again, we have a wall, and we have these sets of handles. This time, all of them are in series. We have one set here on the right, containing, say, vertices from S1, here on the bottom from S2, and here on the left from S3. So every cycle needs to contain vertices from all of them. But again, we cannot really make disjoint cycles in this graph out of this. You can easily, for example, see this because you can add virtual vertices down here adjacent to these paths, down here adjacent to these paths, and down here adjacent to these paths. And then if we would have, say, 3 disjoint cycles, we would have a K3 minor in a planar graph. That's just an easy argument to see it, but in this example, we wouldn't even have 2 cycles. But you can convince yourself of that as well, 2 disjoint cycles. But again, we do have some half-integral packing, highlighted here in color again. But this time, this was actually the starting point of our research like 1.5 years ago. Is this the only other type of obstruction? Do we still have like the half-integral Erdős-Pósa property as in these obstructions for these S1, S2, S3 cycles? And this is one question we wanted to answer. And we wanted to do all of this in a unified setting, that we can talk about about all of these types of constrained cycle results, or a lot of them, in a unified way. And this is what we do with group labelings. So let's take an abelian group gamma and a graph G, and label the edges of the graph G with elements of gamma. The value of a cycle, then we just add up all the edges of the cycle, all the values of the edges of the cycle together. Since our group is nice and abelian, everything works out here without possible ambiguity of what the value should be. And then we prescribe some set curly O of cycles for which we then want to found our large packing, or large half-integral packing, or small hitting set. So group labelings like this have been considered before. So Robin Thomas and Yong-Ho Yo proved the Erdős-Pósa property for cycles in graphs labeled with one of the abelian groups, and the set of cycles they're considering are just the non-zero cycles with respect to that group. And they showed this has the half-integral Erdős-Pósa property. And what we often will do is we consider graphs labeled with multiple abelian groups, gamma 1 up to gamma m, so usually a bounded number of them. And we often view this as, we can view this as labeled with one group, namely the product group of all of these, with then the corresponding product of the labeling. This is sometimes useful. And Hyun, Yos, and Woolen in their paper considered a similar type of thing where they didn't quite look at labelings like these, but at directed labelings, where it for them matters which direction we go through the edge, and going in one direction is the group inverse of the going the other direction. But so these group label settings in some sense have been considered before, and we can encode many possible constraints, natural constraints in such a setting. Odd cycles, of course, we can do by just taking the 2-element group, giving a value 1 for each edge, and then the cycles with value 1 will be the odd cycles. Cycles of length L modulo T, of course, the same with a larger cyclic group, only wanting the cycles of a value L then. Cycles of length at least L, this is a property we've seen before. We can encode here with the infinite group, infinite cyclic group, giving label 1 again to every edge, and forbidding all the values from 1 to L minus 1. We can encode these S cycles that we talked about by, again, using the integers as our group. And every edge incident to a vertex from S gets label 1, and every other edge gets label 0. And then the non-zero cycles in this labeling will be exactly the S cycles. And we can combine all of these. So here, for example, we can encode the odd S1, S2, S3 cycles, which intersect the set S3 at least L times in a natural way, just combining all of these using either these multiple labelings or this product labeling, which I talked about earlier. So this is a powerful way to encode natural properties. And note that in all these examples, here maybe you stumbled across here in the third example that I didn't write length at least L, but I wrote not group value 1 up to L minus 1. With this labeling of giving every edge 1, of course, this is equivalent. But all these encodings work that in a way that we only forbid a finite set of values for each of the finite labelings. And this is something which will now feature in our first main theorem, which comes from the first paper that we've written a year ago, which says that for integers m and omega, there is a function depending on m and omega that satisfies the following. Whenever we have m different abelian groups, or m abelian groups, and for each of the abelian group, we take a subset of size at most omega, subset, let's call it omega I of gamma I, that we want to forbid. So looking then at the graph, labeled with all of these m abelian groups, and as the set of cycles of the graph, which in each of the group avoid the finitely many values in omega, then this class of cycles satisfies the half-integral Erdős-Pósa property. Okay. Sorry? The function, we didn't bother computing it, but no, not the way we proved it. So it's Tower of Ramsey numbers type function. So in this level of generality, we had no intention of trying to optimize this. Right. So about all the half-integral Erdős-Pósa type properties mentioned so far, we get all of these as a corollary. Well, albeit with a much worse function. This dependence on m and omega is actually necessary in the sense that if we label with infinitely many groups, we find counterexamples, or if we forbid infinite sets, we also find counterexamples. Okay. Questions so far? So I want to say a couple words on the proof of this. So if you not understand the statement yet, now is the time to ask. All right. So again, Kevin presented this theorem 11 months ago in this seminar, and you can find more details in his YouTube talk, which is still available on our YouTube channel. but let me at least give the very broad sketch and I will skip some, so almost all of the details, but yeah, the general proof is based on an induction on K. So the size of the desired half-integral packing, and we assume that this function for value k minus 1 is already defined, and we define a function value for k, and assume that in a graph G, the smallest hitting set is much or is larger than this value that we will define for k, with then the goal of constructing a half-integral packing of size k. Step 1 in this would be that a small hitting set will always define us. So if the smallest hitting set is huge, it will define us a large tangle. And just a very brief sketch on how that would look. We also prove that by induction, and this time induction on like the size of the largest packing or half-integral packing of the relevant cycles. So basically what we show, so if T is our smallest hitting set and T is really, so T has size some T, and we assume inductively that that for all subgraphs of G with so where, sorry, I shouldn't write if I don't define too much things. So for all subgraphs of G, if the size of a, so if this subgraph has strictly smaller packings of the relevant cycles than the graph in G, then the size of the smallest hitting set in H is really much smaller. So, well, by a factor of 12, 1/12 smaller. And then we say that every if we take all the separations such that the B side contains most of, let's say, strictly more than 5/6 times T, many vertices of our hitting set, this will define as a tangle. So obviously, if this orients all the separation, it will be a tangle, just because not both sides can have 5 over. So I should say these are all the separations of order T/6 rounded up at most. But yeah, so yeah, so let's give a sketch of the proof. So let's say we have here a subset X of T of size T/6, and here, so let's assume we don't orient some separation AB. So both sides have at least T6 vertices here, and let's say the rest of T is here. So this is T without X union Y, and here we have some small separation of order less than T/6. Then we can easily deduce that the graph here on the left side, so since there is something of the hitting set over here, the graph of the left side must contain a relevant cycle. The graph on the right side must contain a relative cycle. Both of these thus contain less than the whole of G. So we do find a small hitting set here, a small hitting set here. But then these hitting sets, together with everything that was left of our hitting sets and this separator here, would give us a smaller than the smallest hitting set. That's an easy calculation that one can do. So just, we find a tangle with an argument like this, And we know from Robertson-Seymour's graph minor theory that large tangles define as huge walls. So we are already one step there. Step 2 is make this wall nice and homogeneous in some sense. So I don't want to explain the precise sense in which we make it homogeneous, but remember in all these examples we had that since we in all the examples cared about odd length paths in these walls, we had these even length paths between all the nails. So in some sense, oversimplified, you can think the wall has labels 0 everywhere with respect to all the group labelings. This is not quite true, so we only can push it to 0 in some instances. So we need to require to do some shifting for the labels, this is so the shifting would look like, so if we have like some vertex v, and to all the incident edges we add some order 2 group elements. So if 2g is 0, and we add this element to all the incident edges, then every cycle that uses this vertex will not change its value because we add this element exactly twice. And like this, we can basically shift a wall. So if we already have a wall which only has cycles of value 0, we can shift it to be basically a wall where everything is 0 using this technique. And the caveat here, so oversimplified, you are now allowed to think we can always do this, because if we cannot, we can still make sure that we just, that no large subwall has this property of all the cycles being value 0, and then we have a much easier way dealing with everything. But I don't want to go into the details there. Right. Step 3 of the proof is now for this wall, we want to find a large number of handles which allow us to generate group values by using only a bounded number of those handles. This is the step which Kevin talked about at length in his talk, how we can do this. So I don't do too much there, other than telling you we make heavily use of a theorem of Paul Gollin, saying that if we have just group labeled paths, so given some set A, group labeled paths which are internally disjoint to A but whose end vertices are in A have the Erdős-Pósa property. We apply this to the set of nails of our wall, and iteratively we find some new set of handles which for all our coordinates in this product group that we are looking at are either all the same value or all different values. And this is a Ramsey type thing. And if we iterate this long enough, at some point using more Ramsey theory and some clever group theory lemmas, which in part Kevin presented, we will find enough sets of handles that using handles from all of them allows us to avoid one of these finite, so remember in each group we forbid only a finite value. Here we start everything large enough so that we can then always avoid this. So there are a lot of details here that I'm skipping. Feel free to recall Kevin's talk. Right. Last step is then in this wall, we link everything together. And the idea here is, so here we have our wall. Let's say, so we identified now loads of handles that we need to generate our allowable value. In the wall, everything is 0. Let's pick a slice of the wall private for this set of handles. We link all these up to this slice. This slice is big enough so that we can actually build our cycle here. And making sure that every set of handles that we considered gets its private slice. If the wall is big enough, we can make sure that we will be half integral. That's more or less the idea of this linking together. Okay, that's the basic structure of this proof. So what now? What now would stop us to get actually, instead of a half integral packing, an integral packing? And for this, we have again, as I said, all these sets of handles, yeah. So I told you before, for each of the group values, the value of the handle is either all the same or all different. So using like handles from one of these sets of handles, so they come in some sense help us to satisfy the same need in the requirement. So we call if we so we have had in these examples there we can maybe visualize it easier. We had the set of odd handles and the set of S-intersecting handles, and we could we had easy control then over it. Didn't really matter which of the odd handles and which of the even of the S-intersecting we did, as long as we combine them together in the right way. And this is all set up in the step that I skipped, that it's roughly the same idea here. And what we then do is we get some order into these weird set of handles. So basically, from each set of handles, let's say, is extremely huge, so that we can throw loads of them away to get some nice structure. So we want that all the remaining ones are either like this red set of handles here, arranged in the serial way that I talked about earlier, or they're arranged in this crossing way, which I talked about earlier, like in the Escher wall, or in this nested way. And these are really the only three possibilities. Like two simple applications of Dilworth's theorem, if you know Dilworth's theorem, can guarantee us that we can always find one of these three configurations in large sets of handles if we are just willing to throw away a lot of them. And we can also do it in a way that these don't really overlap in a weird way. So we really want that one of the end vertices of all these here, so there is nothing from this series linkage like in between these handles over there. So it really will look something structured like this. This is just some pigeonholing that we can do later. So really no worries there. And what we now want to do is we want to, if possible, combine multiple of these handles. So for example, if we in the proof for the half integral linkage, what I also didn't tell you is, but we can get down that we only need a bounded number of these handles to generate a good value. So we want maybe to just keep iterating here a combination like this. So we can make the wall a little bit smaller, attach two of these together, and get now a smaller set of handles, and maybe now smaller with a slightly smaller wall, and now with these handles, maybe instead of needing 2,000 of them, now we only need one of them because we combined them enough. With this series linkage here, it's pretty clear how we combine this, and we stay like in this series way. With this crossing type of linkage, we can also do this. Like if you follow down here, you can go up here and go back. And interestingly, if we combine like two handles here in the crossing linkage, do it here once and here once, then we end up with a series linkage. Isn't that nice? So basically, if we can combine an even number of these handles in a crossing linkage, then we make out of that crossing linkage series linkage. But if we always need an odd number, we stay crossing. And similar with this nested type of linkage. If we just combine an even number of them all the time, we get down to a series linkage. And if we need an odd number of them, we stay nested. So what we now do is after making every linkage serial, nested or crossing, we try to make every linkage serial in that if it's okay to use an even number of handles to generate an allowable value, then we do that. And if we can't, we leave it nested or crossing. So we combine these handles now together so that whenever we use exactly one handle from each of the handlebars, these were handlebars is our name for these sets of handles. I don't know if I mentioned that before. But yeah, we combine it in a way that using exactly one handle from each handlebar generates us an allowable value, gives us an allowable value. And we can also guarantee by maybe throwing out some handlebars, making some minimality arguments, that if we avoid one of those handlebars, then we cannot, even if we use multiple handles from one of them, we are never able to generate an allowable value. So all these handlebars that we constructed are necessary to generate an allowable value, and they are also sufficient in that taking one handle from each gives us the allowable value. And now we remind ourselves back of the three examples we saw at the beginning. If we have three handlebars which are serial, that was the obstruction for our S1, S2, S3 cycles, then we are in trouble. If we have at least one handlebar which is in series, but not all of the handlebars in series, like in the example of the odd S cycles, then we are in trouble. Or if the number of crossing handlebars that we have is odd, then we are also in trouble, like in the Escher wall. But if neither of these things is true, after we made all these combinations here, then we actually can build a packing of cycles. And this is our second main theorem that I present today, which we are just finalizing the paper, proving this at the moment. So an abstraction now is a wall of order theta, together with a family of these pairwise vertex disjoint handlebars, each of size kappa, say. And the wall has the nice property that the value between each of the paths of the nails, between nails of the wall is 0. Taking one path from each of the handlebars gives us an allowable value. Avoiding one handlebar completely does not allow us to generate any allowable value, even if we allow at multiple paths from all the other handlebars. Whenever we need an odd number of handles from one of the handlebars to generate an allowable value, that handlebar is not serial. So recall when we did do the serialization, if we could do it with an even number, that was one of the steps. And one of the following was true. Again, either 3 are serial, at least one is serial and the other and at least one isn't, or the number of crossing handlebars is odd. And if all of these things are true, then we call it an abstraction. And our theorem now says, similar to this structural theorem of Bruce Reed, that for positive integers m and omega, there is a function fm omega satisfying the following. So every product of m abelian groups, where for each of the groups we have a subset of size at most omega, and every graph labeled with all of these groups and integers k, kappa, and theta, either we have a packing of the allowable cycles, that is the cycles that in each of the groups avoid the set omega I of size at least k, or we have a hitting set for those cycles of size at most fm omega k kappa theta, or third point, we have a subgraph which is equivalent in some sense to one of these abstractions as above, for some subset of the coordinates, and this abstraction does contain the half integral packing for those cycles of size at least kappa. So really structurally, this is an analog of the theorem of Bruce Reed. Okay, questions so far? Good point. It is hidden in, so think of theta as the size of the wall. Yes, the wall is order theta. Right. Yes. Right. So let's. So the nails of the wall are those vertices here that I actually drew. So all these in between here can also have vertices. So basically, this branch vertices of the elementary wall in our subdivision of that are the nails. Okay, so and basically all that what I told you is the sketch of the proof in the level that I wanted to give you. So like combining these handles if possible and so on, and so yeah, I don't really want to now go into that if those don't happen. So if yeah, well, maybe very briefly, if neither of these conditions happen, how can we then actually build the cycles? Well, basically, whenever we have no handlebar which is in series, we can just first of all combine all the handles so that we are left. So combine handles from all the handlebars so that we are left with just one handlebar, and that will then allow us to build the packing. So the idea there is, for example, let's say we have a nested one here and a nested one here. We combine this then into this nested one here. and we, as long as there are no serial linkages in the way, we can kind of always do something like this to combine them. And if we are left with like then only one nested one, then we are basically have an easy way to connect it. Or the other case is that we are left with two which are serial and none which are nested. But then again, it's again easy to see that in this case that one is like here and one is here. We can easily build our cycles like this. And in the case where one is like here and one is here, we can build our cycles like this. So just a very, very brief sketch again to just give you the intuition that if those conditions don't work, everything will work out. I don't have time for a more detailed sketch here, because I do want to talk a bit about corollaries. So Data and Neumann-Lara asked a question to completely characterize for which values of m and l the cycles of length L modulo m satisfy the Erdős-Pósa property. And our structural result actually does this. So basically, the idea is if we take our prime factorization of m, and then the so p1 to the a1 dot 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 pn to the an is our prime factorization of m, then the Erdős-Pósa property holds if and only if whenever so if pi is 2, so if 2 appears in our prime factorization, then the length modulo pi to the ai needs to be 0. And secondly, we don't have 3 distinct primes for which the length is non-zero modulo those prime powers. Right. And a bit more general than this, we could determine of what would be conditions on the group that allow us. So if we have, again, the setting of m abelian groups where we forbid omega many per group, can we have like easy conditions on the group which are sufficient and necessary to have the Erdős-Pósa property, the full one? And here they are, very similar in spirit to the other one. So basically, whenever we have that value a is allowable, we want that 2 times that value generates us something allowable. And whenever we have 3 allowable values, or better say, whenever we have 3 values which together generate something allowable, then already 2 of them generates something allowable. And this will be sufficient and necessary to get an the Erdős-Pósa property for those cycles. Here we can also make slight modifications. So we remember many of the examples that I told you in the beginning, we could just add, and those cycles have length at least L. So even cycles have the Erdős-Pósa property, and we can just add of length L. And this corollary kind of formalizes is that something like this, some property like this, we are always allowed to add. What do I mean by this? Well, if for some of the groups that we are labeling with, the graph has the property that every wall contains a cycle. So every large enough wall in that graph contains a cycle whose value in that coordinate is non-zero. So, for example, in the case where we cared about the length, so there our group was the integers and every edge got value 1. So of course, no, for this labeling, we will not find a wall without zero value cycles, because every cycle will be represented by its length. Then these are group labelings for which we don't need these two properties. So basically, we divide the groups into two sets. One set for which we have the two conditions as before, and another set for which we just don't have the walls without zero cycles, and then we still can say that we have the Erdős-Pósa property. Okay, thank you.
Can you show the first corollary?
The first what?
First corollary.
Yeah.
I think it would way good statement should be like for L and M.
Mm-hmm.
Whenever there is F subset blah blah, then L and M should satisfy the below two.
Oh.
Is it a typo or
Oh.
just a reason?
I see. So yeah.
Wait, what is typing? So for all integers L and M, if we have this prime factorization, then we have the Erdős-Pósa property for the cycles of length L modulo M, if and only if L and M basically satisfy these two properties.
But I see his point. In the sense that if and only if it's in the sentence inside the like there exists function. So but what we really meant was that there is this function if and only if this condition is called. Right now it sounds like if and only if it's only for G contains K but this cycle or Fk. So f of k is the existence of function is outside the if and only statement. So
Right. So I mean,
Oh, I see.
yeah.
yeah. So
Yeah.
I agree.
Yeah.
Yeah.
I think it's equivalent.
I think it's equivalent. Yeah.
I see the point.
Yeah.
It could be, yeah.
In some,
But maybe there
in
could be
some
some
strange way.
there could be some silly function that the first part could be false, right? And then that's weird, right? So, but this whole thing says that there is this function,
Yeah.
which is huge anyway.
Yeah. So I think it's really equivalent. Yeah.
But yeah, there is an interpretation which is strange and one.
Yes.
Yeah.
And
Yeah.
it could make it more clear.
Right.
which
Yeah.
one we-
Right.
Yeah.
Right. More questions?
Is it possible to make some directed graph with the non-abelian groups?
So with non-abelian groups, we need to be a bit more careful because of what. So with abelian groups, we had an easy way of defining what is the value of our cycle. In non-abelian groups, that's no longer well defined. So maybe recall that I did tell you that that Tony, Felix, and Paul did some stuff with directed labelings. They actually considered non-abelian groups in their paper, but they could do that. So they could do that because they only cared about cycles of value non-zero, because basically the starting point of where we start to sum up the value of the cycle is so if we only care about non-zero cycles, the starting point doesn't matter. The value of the cycle may change, but it wouldn't change to 0 or away from 0. But this precise value of the cycle could change.
Yeah, this seems to be a much harder question. Well, it seems to be a harder question that we don't know.
Changing the starting point is only the conjugate.
Yeah.
Maybe one potential question is like we have an argument.
Well, in a sense, yes. I think all the tools that we are using do have algorithms, and our proof could be considered algorithmic, I think. But it wouldn't be any type of algorithm which ever would be feasible, I think. I'm also not 100% sure on this, because we are hiding things in induction type proofs. But I feel like there's an algorithm there.
I was imagining that there could be a shortcut for algorithm.
Right.
Could you give me any simple example which says
Well, yes. So as I told to you much earlier, here's our half-integral theorem. The dependence on m and omega is necessary. So, for example, let's say you have graphs labeled with infinitely many abelian groups, say. Yeah, I think what we probably can just do is infinitely many copies of Z2, the two-element group. And we want to look at the, what do we want to do?
Maybe cycles of weight 0?
Yeah, cycles of weight 0 in that group should fail the half-integral Erdős-Pósa property. And what could be the example?
Might be easier to do Z2 times Z3 times Z4 times Z5. All there. We're all fine. The product of these groups. So then suppose that we're looking for cycles of weight 0 in this. Now, if I have a graph where I choose the first k coordinates, and every edge is going to get weight 1 in each of the first k coordinates and weight 0 everywhere else.
Right.
Now, cycles which are sufficiently long will all have 0 weight. So if their weight is like k factorial or something, if the length is k factorial, then they'll have 0 weight. But if they're short, they won't have 0 weight. So if you make the size of the graph, if you pick the size of the graph so that all long cycles intersect, then you can't hit the long cycles with only a bounded number of vertices, but you can not fit two disjoint.
Long
But every 3 cycles will still intersect. So you can, if you make it so that the shortest cycle of 0 weight has length 2/3 n, more than 2/3 n, so about say 3/4 n, then every 3 cycles will share a vertex. If so.
The thing with this is you just need to work out the precise numbers and then it's clear. We did this in the paper. It's just recalling the right numbers is not always the easiest. Right. And in a similar vein, in a similar idea, we can basically. So one could also, of course, try to generalize half integral to 1/3 integral or 1/4 integral. And with similar constructions, we would get something like, which satisfies the 1/n integral Erdős-Pósa property, but not the 1/n plus 1, I think. I think similar construction would work.
Wait, that actually satisfy the 1/n?
You come up with a specific
Yeah.
specific family of graphs and specific family of wavelengths.
Yeah.
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 If you don't not try and just specify the group.
Yeah. So we would need to restrict the class of graphs we're looking at as well. At least for this type of thing. Yeah. Yes.
For the theorem of Thomas and Liu.
Yep.
For the first main theorem, this is for the group labeled graph means the group is labeled on the edge of the graph.
Yes.
And can we think of some group labeling on the vertex of the graph?
Yes. So basically, everything which I did here about labelings of the edges, you could turn into an equivalent problem of labeling on the vertices. So there's a more or less straightforward translation that you can do. So in one direction, you can just subdivide each edge, and this new vertex gets the vertex label from that edge, and all the old vertices get value 0. That would be the translation in one direction. The translation in the other direction is a bit more complicated, but yeah, if you're interested, we've written it down in our first paper, that translation. No.
Oh, you don't change the graph, you just move the weights onto the edges.
Right.
Yeah.
So
Yeah.
like if you've got a labeling in Z3 on the vertices, you can translate to a labeling on Z6 on the edges.
Yes.
That sort of thing.
It's not too complicated. But the important thing is that with this translation we capture the same class of cycles, and this is why all our theorems will be equivalent in that setting. Then.
Okay, let's thank the speaker.